Hey everyone, welcome to science class this week. Today we're going to be starting on the geologic timescale because we have just wrapped up the dynamic crust unit for this. So geologic timescale is a way that humans have recorded different time periods within the Earth's very, very long age. So you could see on this little mountain here, down here, the Earth formed about 4.6 billion years ago. And then up here are where the humans currently are. So the timescale is our way of trying to figure out what happened between the Earth forming 4.6 billion years ago and us. Obviously, to record 4.6 billion years of time is really long. You could just think about how long 50 years ago was, That is nothing compared to 4.6 billion years. So it's a lot of information for us to try to discover. So in this lesson, you're going to pretty much learn the ways that, the main ways that we've actually been able to piece this puzzle together. And it's still going on today and constantly changing and being reformed and things like that. So here we go. So this looks obviously like a lot. Because it is. If I were to just pick out a couple of things on this geologic timescale, and you're going to see throughout this presentation, there's a lot of different ways that we have organized this data, but it's just pretty much a way of classifying different time periods. So we gave them all names. You could see, like, you might have heard of Jurassic, Triassic, maybe Cretaceous up here. You might have heard of that before. But you might not have heard of some of the other ones, like Tertiary or Neogene or Cenozoic. Like, you might not have heard of that before. And all that is a certain time period in the Earth's long age. And we separated them into these time periods based on similarities of things. So this could be a lot of things. The main one is fossil evidence in types of different rocks that were around at that time period, different plants in that time period that were only in that time period, major events that might have happened in that time period, like maybe an asteroid hitting the Earth. Like, the asteroid hitting the Earth could have ended a time period and been the start of the next time period, because obviously an asteroid wiping out 99% of life, the next time zone after that is going to be like a different world, essentially. So that's sort of like how we're breaking this up. And then you can break up that into 4 different time periods and that into different time periods. So it's just a way of narrowing down different time periods based on similarities. So here's a little example. You could see the newest is generally on the top. So you could see 0 years are on the top. And this only goes down to like 450 million years ago. So you could see 450 million years ago, the era right here, the era was called the Paleozoic era, and the Paleozoic era was broken up into like this section and down. And just some of them. So we got different time periods up here in the eras. So the Paleozoic era was broken up into the Permian time period, the Carboniferous, the Devonian, the Silurian, and the Ordovician. Well, what's different about the Ordovician period compared to the Devonian? Well, you can look at some of the events. So in the Devonian, we got our first amphibians. Our jawed fish with jaws started becoming more diverse, meaning there was more of them. In the Ordovician, there was more metazoan families, which is a type of organism. In the Silurian time period, we got our first vascular land plants. So like this event here, the land plants, was considered so important that they made its own time period based off that event happening. Like, look at Jurassic. What's so important about the Jurassic? Well, that's when our first birds were ever made, essentially. Dinosaurs are starting to become more diverse, meaning they look very different. But then look at the Cretaceous. The Cretaceous started here. So we got our first flowering plants. But then look, over time, the end of the Cretaceous, the dinosaurs went extinct. So that marked the end of the Cretaceous. And they actually thought that was so important that they started a whole new era called the Cenozoic era. And this is what we're currently in. So you could see the Quaternary period in the Cenozoic era right here. That's when we were around. Now, actually, don't quote me on this one, but I'm pretty sure we actually might have entered a new time period in the last 10 years. I think they made one due to global climate change. The fact that the climate was changing so much due to humans that they actually considered that entering another period of time, but I gotta look that one up. All right, so that's generally the idea. So you can see there's another picture of it, but geologic timescales are created to organize data to better understand the age of certain creatures and structures on the planet. So even though you've got an example of different animals that are within each time period, we also can talk about what things happened on the planet. Maybe a certain mountain was formed. Maybe a certain river was formed, and that could be an event that changed a time period. So you got eons, which is the biggest, an era, which is the second biggest, and then eras are broken up into time periods, and periods are broken up into epochs or epochs, however you want to pronounce that. So it's just getting more specific, more specific, more specific. So here's just another example. In the Quaternary, let's do Paleogene. In the Paleogene time period, it's broken up into 3 epochs: the Oligocene, the Eocene, and the Paleocene. And this is the millions of years ago that it was. So the Paleogene started at 65.5 million years ago. What was the major event that happened at 65.5 million years ago? Well, if you look here, it was the mass extinction of dinosaurs. This is when all the dinosaurs died. So they started it was the end of the Cretaceous and the start of the Paleogene. And then you could see like 15 million years later, you get mammals, then your grass, and then you enter the Neogene, and you're going to get grazing mammals, carnivorous mammals, and then finally the Quaternary is when humans, mastodons, and mammoths started being here. All right, so here's the question. I'm showing you all these charts. How did we figure this out? Well, that's where relative dating and absolute dating comes in. So it's certain dating techniques where we test something or compare it to something else to figure out how old it is. So the major way we could do this is that the same processes that are happening right now on Earth are the same processes that happened throughout the whole Earth's time period. The way that a rock breaks down today is the same way that a rock broke down 3 billion years ago, essentially. The way that plants die and get buried under the ground, it's the same exact way that it happened 3 billion years ago. So we can use what we know today to understand what happened 3 billion years ago. And one of the ways we do it is called radioactive decay. So what we do here in a nutshell is all substances are made of atoms, and we find certain atoms in the substance and they deteriorate at a certain rate. So say you look into a fossil, right? You have a smiley face fossil here, right? And you're like, oh, I found a smiley face fossil. I want to know how old this is. Well, they could take an instrument and they can look inside of the fossil for a carbon atom. And what they could do is they could see how much of the carbon atom is left. And based off that, they can figure out how many years old this is. So depending on what they look for, isotope, just you could think of an isotope as an atom. They could look for carbon-14, potassium-40, uranium-238, rubidium-87. These are the 4 main ones. All of these have a certain age, a certain length of time that it takes for them to start disappearing. So if we look inside of them and see how much is left, you can backtrack and figure out how long it took. Another way they can measure age is by looking at volcanic ash layers in rock. So you could, if you're in a helicopter and you look at this picture, do you see this black line right here? that was a volcanic eruption that happened in the area. And you could see it's like jet black. That's the ash layer. So we can actually use the ash layer to determine the age of rocks around it. So we could say this rock down here must be older than the volcano eruption because it's under it. Anything on the bottom is older. And this up here must be younger. And they do this essentially, it's a little bit more complicated than that, but this is like some of the tactics they use to piece together the puzzle of the age of the Earth. Another one that you're definitely familiar with is fossil evidence. So they look at certain fossils, they radioactive date these, and they could see how old it is. Then they look at what type of rock it's in, and they can match this type of rock with another type of rock on the other side of the planet. It's pretty cool. So there's all different fossils that they can find, right? They can find these things called trace fossils, which are like footprints and stuff like that. They can find molds or casts, which are the ones that you're probably most familiar with, or replacements. You could see what they look like. Generally, a mold or cast is like an imprint. And then a replacement is when the bones of the fossil were replaced with minerals, so it looks like the actual skeleton. You can find petrified wood, which is, again, replaced by minerals. Amber is when it's like tree sap and it drips down and it traps the organism inside of it, which is pretty cool. Or, in the rarest case, the original material of the specimen, which can also be more common in ice. Ice preserves original material. All right, cool. So it's just an example of some fossils that could be found, and you might be wondering how that was actually formed. So we're going to end this little lesson with a quick video. I think it's from the Museum of Natural History. I thought it did a good job of explaining like how a fossil is made. Okay?
Millions of years ago, this dinosaur was going about his normal daily life. But his day went from good to bad. Really bad. After he died, other dinosaurs ate him, and the rest of his skin and muscles rotted away, leaving just his bones. These were quickly buried by mud. Over millions of years, more layers landed on top: mud, sand, and even volcanic ash. This added up to a lot of weight on top of the skeleton. Some parts got crushed. The layers of mud, sand, and ash turned into hard, sedimentary rocks. While this was happening, water seeped into the bones. It left behind minerals, turning the bones to stone and creating a fossil. Earth changed a lot over millions of years. Rocks that were once deep underground rose to the surface, a process called uplift. Very slowly, wind, water, and ice wore away the rock. Eventually, bits of the fossil skeleton were exposed and became visible on the surface. Fossils are constantly getting eroded out of rock. Most are lost. But if we're lucky, someone will find one. Yippee! Nearly all of the fossils we find, around 99%, are from marine animals, such as shellfish and sharks. This is because they lived in the sea, where sand or mud could bury their remains quickly after they died. But dinosaurs live on land, so how do they get buried so quickly? Most dinosaur fossils we find belong to animals that were living near to a lake or a river. They died, and a short while later the area flooded, covering their remains in mud and silt. Occasionally, something more dramatic happened. In one example, two dinosaurs, Protoceratops and Velociraptor, were fighting in the desert. They were mid-battle when, suddenly, a sand dune collapsed on top of them. Their fossils show them frozen in their fighting poses. In another tragic example, the feathered dinosaur Sittipati was sitting on its nest of eggs when a sandstorm blew in and covered it. Fossils like this, from animals that were alive when they were buried, are really rare. It's not just bones that turn into fossils. Dinosaurs can also leave behind footprints and impressions of skin and feathers. So next time you're near some sandstone or mudstone, think of what fossils could be hiding, just waiting to be discovered. It probably won't be a dinosaur fossil, as they're so rare, but it could be a prehistoric sea creature like an ammonite, which went extinct at the same time as dinosaurs many millions of years ago.